Okay, our program for tonight, Brad Hoehne. Brad Hoehne is going to be doing his presentation on the history of telescopes in space. So, Brad, you want to go ahead there?
Sure. I was interested in this particular topic because I'm kind of a space head and have been following the James Webb Space Telescope as it successfully deploys out at the L2 Lagrange point out past the orbit of the moon, about 1 million miles beyond the Earth. And I'm really excited about the imaging that is going to come as a result of that. So I thought I would go back and actually take a look at the history of telescopes in space, and it's rather extraordinary. I mean, there have been literally dozens and dozens of space telescopes, and most of them you probably haven't heard of. So what I wanted to do was go through and tell you a little bit about some of the various space telescopes that have been put into orbit and on rockets and on balloons and such, and why those particular space telescopes were sent into space, why you can't actually do what those space telescopes do down here on the ground, what makes it worth putting a space telescope into space. So let's talk a little bit about why you would put a space telescope in space. First of all, it's really expensive. I mean, one of the issues is you have to buy a rocket, you have to send it up into space. In general, a space telescope costs at least hundreds of millions of dollars. I mean, it's a rather elaborate process. So why would you go to all the trouble and all the expense of putting something into orbit? Well, the most common reason is the fact that we live at the bottom of a giant swimming pool full of air. I mean, if you look up at the night sky on any given night, you will notice that the brighter stars tend to twinkle. And as a result, if you were to actually magnify an image of a star or a galaxy or whatnot, the view of that object is going to be blurred by our own atmosphere. Our own atmosphere actually gets in the way of imaging by smearing out the process. This is a process called scintillation, and what it does is it takes the ideal star image. This is actually a figure called an airy disk. If you took a star and you had absolutely perfect optics, you had a perfect refracting telescope or a perfect reflecting telescope with a very small secondary mirror, and focused it on a star, this is the image you would see if you blew it up. You would actually get a bright center, and then you would get these fainter rings around it. This is absolutely the most perfect image of a star you can get. Unfortunately, our atmosphere actually has problems here. There are, as you go up higher and higher, you reach turbulent areas of our atmosphere. This tends to be because as you go up, the atmosphere actually changes in temperature, and the warmer air from the bottom of our atmosphere mixes with the cooler air from the top and creates kind of an interface between the steady air way up high and the relatively steady air down below. And what happens is light that passes through the region where warm turns into, or cold turns into warm, the light waves actually get perturbed. They actually jostle around the view of a star. So you get what are called perturbed wave fronts. And this is a result of the temperature variations in our atmosphere. Let's take a look at what that looks like. Here's the picture of a crater on the moon. This is the crater
Brad,
Yes.
Brad, you're not sharing your screen.
I'm not sharing my screen. Oh, okay. Sorry about that.
Brad, you can see it on Facebook, but we can't see it in Zoom.
Oh, okay. Let me share my screen. I am so sorry. Let's take a look here. Share. I forgot. See, I have so many different things I have to do. So here is my screen. So I'll show you the pictures. Here's my metaphor for living at the bottom of a giant swimming pool of air. Here's the airy disk. Here's the turbulent layer. And this is what it looks like when you're looking through a telescope when you're at the bottom of a giant swimming pool of air. This is actually the crater Clavius on the surface of the moon, and this is a pretty normal view of what you would get of the night sky. And this is a view of an individual star. And you'll notice that the star doesn't look like one of those little perfect airy disks. It's actually smeared around. It doesn't look like this. It's rather difficult to see the form of the star. Now, it is possible to actually, from the ground nowadays, cancel out some of this with something called adaptive optics. What astronomers will do is they'll fire a laser beam up into the sky, and that will make an artificial star up on a layer very high up above the ground. There's a very thin layer of sodium atoms that are many miles up above the surface. It's usually around 30 to 40 miles up. A lot of that is dust that is deposited by meteorites. And if you fire a laser up at that layer up in space, you can actually make a star. And since we know exactly what that star ought to look like, the astronomers can manipulate the mirror of a telescope to take that artificial star and bring it back into perfect sharpness. Now, this process is not 100% accurate. I mean, you can't take out all of the problems with Earth's atmosphere, but you can get some pretty good views. This is actually a before and after picture taken from the Keck telescope of the planet Uranus, and you'll notice that the one on the right, where adaptive optics is applied, is much sharper than the one on the left, where adaptive optics is not applied. Now, there is a problem with this. This system tends to work best in the near infrared. At higher frequencies, where you're dealing with blues and that kind of thing, it's more difficult to actually use adaptive optics. So it's not a fix-all. It's not a universal solution. So here's a picture of Saturn. You can see that Saturn actually gets a lot better. This is from the Pico de Midi Observatory on top of a mountain in France. And to compare this particular image, this will show you why we actually go. One of the reasons why we go into space. This is a picture from the Hubble Space Telescope. Now, notice how much sharper the image is. Even with adaptive optics, we're still getting better. We're still getting better clarity from telescopes in space. Here's a picture. Adaptive optics have actually gotten a lot better in recent years. This is a picture of an area in Monoceros. You can see that the image is fairly sharp. Now, this is a pretty wide field of view. This is from the Gemini telescope, and this is without adaptive optics down here at the bottom. Another reason why we can get good and sharp images. So this is not the primary reason why people throw space telescopes up into space, because nowadays we can actually get fairly good sharp images from the ground with interesting techniques. But there are other reasons to put telescopes up into space. One of them is light pollution. Now, this is a picture taken in the Atacama Desert in Chile, and you will notice that even though the Atacama Desert in Chile is probably about the darkest place on the planet Earth, it's high and dry, very few clouds, you'll notice that the sky is never 100% dark. If you take a really long exposure of the night, you'll still get some light pollution from the natural environment. The Earth's atmosphere is never 100% dark. There is a phenomenon known as sky glow, which is caused by the sun striking the molecules of gas in our upper atmosphere, breaking up the molecules, and then over the course of the night, those molecules form back again. Nitrogen will get broken up into 2 nitrogen atoms, and then the nitrogen will stick back together again, creating a little bit of light in the process. And over the course of an entire night, that process will just continue on over the course of the evening. And so the sky will not be entirely dark because all those photons of light will be hitting the ground. So if you want to take really, really deep pictures of very faint, very subtle nebulae and that kind of thing, you can't do it from the ground very well. Here's a picture of some aurora right here, which is also an issue. But if you look over here on the right, you can actually see this continues on. That is actually that sky glow. And I would be curious to, any geography buffs would be able to tell me where this is. I know where it is. But if anybody wants to speak up, they'll get kudos for knowing where this is. And I'll tell you where it is in just a sec. Scandinavia, exactly. This is Denmark and Norway, or Denmark, Sweden, and Norway. So, nice job. The real reason that the most important reason why space telescopes are important is because we here down on the ground can't see all of the light of the electromagnetic spectrum. Only a small portion of the light that hits the top of Earth's atmosphere reaches the ground. This is a little chart here which shows you how far the light actually penetrates and how much of the light actually gets through to the ground. This right here is the visible spectrum that we're used to. Most of the visible spectrum makes it to the ground. About 90% of it makes it to the ground, and a little bit of it is scattered away. And then as we go to the right here in this graph, this goes toward the infrared and then the radio region and then the long wavelength radio region. You'll notice that a lot of the regions of the infrared are heavily blocked by Earth's atmosphere. A lot of this region here, which is called the sub-millimeter region, that's blocked almost entirely except for this one little nook right here. Radio, a good chunk of the radio spectrum makes it through, but if you go to really long radio wavelengths, it tends to get knocked off. It tends to not make it through. Anything greater than middle of the road ultraviolet is completely blocked off. We cannot see, thankfully, the X-rays and most of the ultraviolet spectrum from space. If we could, it would be bad news for us because we are soft and vulnerable human beings, and our cells are affected a great deal by X-ray and gamma ray and ultraviolet radiation. And if it made it down through to the ground, we would be in trouble. So what I'm going to do is take you through the electromagnetic spectrum and tell you the history of space telescopes from the point of view of the electromagnetic spectrum. I'm going to start with the shortest wavelengths, and I'm going to go to the longest wavelengths. Why do I do that? Because I just picked that particular direction. So let's get started. I'm going to tell you a little bit about why those particular regions are interesting, what you can observe astronomically speaking in those regions, and what those particular regions of the electromagnetic spectrum do for us down here on the ground, and how they are interesting to us in other ways. So I'm going to start off with the gamma ray spectrum. The gamma ray spectrum is the shortest wavelength of the electromagnetic spectrum, and they are the highest, and gamma ray photons are the highest energy photons in the electromagnetic spectrum. If you were to be hit by a gamma ray photon, it would cause damage to your DNA, to your cells, and that kind of thing. They're extremely powerful. If you were to be hit with a blast of gamma rays continuously, it would kill you. Not a good thing to be exposed to. Gamma rays, astronomers will often refer to gamma rays not in terms of their frequency. Their frequency is defined by being anything less than 1 nanometer, their wavelength is defined by anything being less than 1 nanometer. Gamma rays are often expressed in units known as electron volts, and this is how much energy these photons have. And the reason why they do this is because the way you detect gamma rays is by how much energy they impart onto a system, and I'll tell you about that in a little bit. So generally they'll talk about gamma rays in terms of how much power they have, how much power those photons have. A gamma ray is also defined as anything greater than 100 kilo electron volts. That's anything that's less than 1 nanometer is higher than kilo, 1,000 electron volts. The highest level gamma rays are up in the giga electron volt range, and they go even higher than that, but that's about as high as we can detect. Gamma rays in the universe are extremely rare. In fact, if you have a detector, it has to gather gamma rays for a really long time for you to actually make an image of gamma rays. So what do gamma rays come from? They tend to come from cosmic ray bombardment. So there are particles that fly through space at very close to the speed of light. They come from supernovas, they come from black holes, and that kind of thing. And when those hit solid surfaces like the moon or like the Earth's upper atmosphere or gas between the planets, that actually produces gamma rays. The energy of those individual particles is so great that the gamma rays are produced. Supernova and neutron star mergers also produce a lot of gamma rays. So those are two forms of supernova, incidentally. And when a star explodes, its energy is enough to produce, very briefly, a blast of gamma rays. Black holes, which are the result of some supernovas and which also occur in the cores of galaxies, also produce gamma rays in their accretion disks. If a black hole is absorbing a lot of materials, that material will actually, right before it falls into the black hole, will be producing an awful lot of energy, and some of that will be in the form of gamma rays. And also, relativistic velocity gas collision. What does that mean? That means that gas that is colliding with other gas at very close to the speed of light, that will produce gamma rays at a very low level. And at higher than 30 giga electron volts, extremely high energy gamma rays can actually produce showers of secondary particles. So we actually get particles down here on the ground, from gamma rays that are hitting our upper atmosphere. So we can detect gamma rays indirectly as a result of them hitting our upper atmosphere and producing interesting showers. So the history of gamma ray astronomy starts off with the nuclear era, with the nuclear weapons era. Back in the early 1950s, late 1950s, people were looking for a way to determine whether or not our enemies were testing nuclear weapons. And so a system was devised called the Vela system, that was a number of individual satellites that were put up into space and to detect the characteristic gamma ray blast of a nuclear explosion. A nuclear explosion can actually cause gamma rays. It's one of the few human-made things that can make gamma rays. This is a picture of the Vela satellite here. There were several dozen of them over the course of their long history. Interestingly enough, the Vela system unexpectedly detected what appeared to be nuclear explosions every couple of days. It actually detected large blasts of energy that would otherwise have been produced by a nuclear explosion, but instead they were actually coming from space. So for a long time, the U.S. military kind of sat on this information. General astronomers were not aware of the fact that there were gamma rays that were out there in space. However, gamma rays were of interest to astronomers because we wanted to learn about the very high energy universe. This is a picture of the universe in gamma rays. There's a lot of individual little sources of gamma rays. Most of these are the cores of massive galaxies, and the line here in the center is relativistic collisions between gas and cosmic rays hitting the gas between the stars. This is extremely faint, so it takes a very long time to take these exposures. So the very first satellite that was actually put up to study gamma rays was the Compton Gamma Ray Observatory. This was the one that was actually an astronomy tool for observing for gamma rays in space. And the Compton Gamma Ray Observatory covered much of the gamma ray spectrum here from, I won't actually read off the numbers, but this is the region that the Compton system detected. And it was the first system to actually pick up on these blasts of gamma ray energy, which they called gamma ray bursts. They occurred in every day or so in space. They lasted anywhere from a millisecond, 1,000th of a second, to several minutes in length, or perhaps even a little bit longer. And the energy that was being put out as a result of these, if these were extremely far away, would be the equivalent of, it was determined that the equivalent energy of our entire sun converting itself into energy all at once. That's how much energy these gamma ray bursts were coming from. It wasn't really understood for a very long time what gamma ray bursts were, however. So gamma ray bursts are detected in a very interesting way. You can't just get a big lens and focus gamma ray bursts. So what I'm going to do here over the course of this talk is talk to you a little bit about the technology that is used to perform these detections, because it's not always as you would expect. This device up here is a stack of what's called a spark chamber, and this was in the Compton Gamma Ray telescope. So what happens is a gamma ray will pass through this system. A gamma ray will hit and pass through, and it will actually hit this area, which causes the gamma ray will actually pass through a block of material, which will shower electrons and positrons down through this region of detectors here. This was actually a stack of individual detectors, and as it passed through these individual detectors, the position that these things would hit the detectors would actually be noted. Now, the electrons would actually get deflected from side to side as it passed through these individual detectors, and that is an interesting thing in and of itself. However, the direction of this gamma ray could actually be roughly determined within a half a degree or so as a result of which part of the detectors it hit. If you wanted to know the frequency of this gamma ray, you could know the frequency by how much deflection there was between each hit of these detectors. So if the gamma ray got deflected a lot more from side to side, then it was a slightly higher frequency gamma ray, and if it got deflected a little bit less, it was a lower frequency gamma ray. And this is the method that is used to detect gamma rays. You point your detector in a given direction and you watch the secondary particles that pass through the detector. Now, this is not particularly precise. You can't make very high resolution pictures this way, but you can get a general idea of where the gamma rays are coming from in the universe. There are detectors that are being set up on the ground. This is actually a giant detector that's being set up in South Africa, and what ends up happening is a gamma ray will hit our upper atmosphere, and that'll produce a bunch of showers that'll come down and hit the upper atmosphere and produce a very faint glow of radiation called Cherenkov light, and this will these things are just very high sensitivity detectors that will pick that up. So you can actually do this from the ground, but you can't detect the individual gamma rays themselves. You only detect the indirect evidence of them. So this is a picture that the Compton Gamma Ray Telescope took. It was the first one that they sent up, so it was very, very low resolution. They were able to get a rough idea of the gamma rays in space. Another target of the Compton Gamma Ray Telescope was the Earth itself. They actually pointed the Compton at Earth and saw the effect of these cosmic rays hitting Earth's atmosphere. And this is a picture of the gamma rays hitting the Earth's atmosphere at different frequencies. This is 35 mega electron volts, 100 mega electron volts, and more than 1 giga electron volts. Very, very high energy gamma rays. And this is a color picture that combines all three of them. So this is a picture of, believe it or not, the moon. The moon gets hit by a lot of cosmic rays, and those cosmic rays produce gamma rays. which can be detected. Now these pictures take hours and hours to compile because gamma rays are extremely rare and very weak, or at least the flux of the gamma rays are very weak. Individual photons are quite strong. So getting back to those gamma ray bursts, starting in 2004, there was a satellite system known as the SWIFT that was sent up in order to detect gamma ray bursts and figure out roughly in what direction they are coming from. There was a system on the ground that was designed to follow up on these gamma ray bursts and see if there was some other light that was coming from space in that general direction. So if they found a gamma ray burst in space, they would instruct the telescopes on the ground to scope out the general area that the Swift telescope found these gamma rays in, and gamma rays coming from, and they would then see if there was a star that was slowly dimming after it had exploded. And they determined that a lot of these gamma ray bursts work from stellar mergers, neutron star mergers usually, that were coming together and exploding. And so these bursts are actually coming from all around the universe. They are extraordinarily powerful explosions and amongst the most energetic things in the universe since the Big Bang. They are another thing that the SWIFT actually detected was the jets of distant quasars and merging stars. Occasionally, what would happen would be there would be a stellar merger, and those stellar mergers, the energy of that produces a very strong jet. And if we happen to be in the line of sight of that jet, we get a very, very powerful burst of gamma rays that actually point.
Brad, can I ask a question?
Sure.
If we go back to the previous slide,
Correct.
Yeah. It seems like it's generalized. It's coming from everywhere. Is that right?
That's right.
There's no part of the sky where we might see more.
Right. The reason why, that's actually a very good point. The reason why we know these things are coming from a great deal very, very far away is that they are not lined up with the Milky Way. They're not actually coming from within the Milky Way. They're coming from the distant intergalactic universe. Because they are what are called isotropic. They're coming equally from all over the sky. If they were coming from our Milky Way, you'd see them bunched up along the plane of our Milky Way. So these are coming from distant galaxies. And so that tells us that these things are, they're relatively rare because we're not getting them from our system. But the universe is very, very large. And so, there's enough volume in the universe for us to get, one or two of these a week, or every couple of days we'll get one up in space.
And so the effective exposure time here is 11 years?
Yes, this is an 11-year collection of all the SWIFT detections of gamma ray bursts. And it works out that you get one every couple of days. That's kind of, so if you're up in space, there's a blast of gamma rays every couple of days. And that's something, if you're up in space, that's a bit of a problem. So Swift also was able to determine the formation of black holes at the end of very massive star lives. When a star actually collapses, when the core of a star actually collapses at the end of its life, it very briefly makes an accretion disk before it very briefly makes a disk of material that is falling into it, and that disk of material actually produces a jet. And if we happen to be in line with that jet, we get a very, very intense blast of gamma rays in our direction. So this tells us that these events actually occur a little bit more than what quite a bit more than what we think, because we have to be in line with the jet for us to see a gamma ray burst. And once again, neutron star mergers are one of the main causes of these gamma ray bursts. So the next area of the electromagnetic spectrum is the X-ray spectrum, which is something we're probably a little bit more familiar with. X-ray tends to be produced by very hot gas and plasma. You get a lot of gas between galaxies when the gas is colliding at very, very high speeds. It produces X-rays. There are there is gas that is colliding at very high speeds in the corona of our sun. The very low density corona of our sun produces a lot of X-rays. Supernova remnants produce X-rays, the shock waves of supernova remnants. So when the Crab Nebula exploded a long time ago, that the shock wave of that going out into space hits the gas between the stars, and that actually produces X-rays. Neutron stars themselves also produce a lot of X-rays. The surface of neutron stars are extraordinarily hot, and they're hot enough to produce neutron stars. Accretion disks, once again, just like gamma rays, are also produced. Quasars and black holes, which are basically just accretion disks. Interestingly enough, Jupiter's Aurora produces a very low level of X-rays, and between the stars, if you have a supernova that produces radioactive elements, as those radioactive elements decay, that actually produces a very low level of X-rays as well. Astronomers will typically divide X-rays into two types, one called hard X-rays and another one called soft X-rays. Hard X-rays are X-rays that can penetrate us, basically. And soft X-rays are less energetic X-rays, basically. So hard X-rays, if you go to you go to the doctor and you get an X-ray or get a CT scan, those are the X-rays that they actually use to create an image of your bones or your insides and that kind of thing. Soft X-rays would not penetrate your body as much. So this is a map of the sky in two different frequencies of X-rays. The blue is the hard X-rays, and the green are the soft X-rays. You'll notice the green actually kind of comes. The soft X-rays are from gas, and that is a result of a collision of gas at very high temperatures. And the blue region comes mainly from the hot stellar remnants, like white dwarfs and neutron stars and that kind of thing. Those tend to produce a lot of X-rays. So all told, this is what our night sky looks like in X-rays. You'll notice that there's a lot more X-rays in our Milky Way galaxy than there are gamma rays in our Milky Way galaxy. There's a lot. The gamma ray sources tend to be extragalactic, come from the cores of galaxies, and X-rays come from all over in our own galaxy. So the history of X-ray astronomy goes way back to the very early days of putting telescopes in space. In fact, the very first space telescopes were X-ray and ultraviolet telescopes, and this is because astronomers wanted to get up and out of the atmosphere in order to see what the heck was out there. And one of the very first things they did was they would send up sounding rockets, which are these rockets which go anywhere from 100 to 200 miles up above the atmosphere. They make a big arc and then they come back down. This is one called the Aero B-150, and it went about 160 miles up. And this is the payload. This is actually a payload that was designed to detect X-rays, and this system was actually invented in 1963. So the very first space telescopes were not orbiting around the Earth. They were actually sent up very high above the atmosphere and made their first detections in short flights. In fact, usually they would get about 5 minutes of detection before it would come back down.
Brad.
Yes.
Were they ballistic, kind of like Alan Shepard's?
Yes, they were like suborbital.
Going up, going down. That's it.
That's
or
right. They were
William Shatner's. Well, he did orbit, but then he came back down in 10 minutes.
Exactly. They're very much like the William Shatner suborbital flight. Basically, it was about the same amount. So the payloads. The payloads would make a suborbital flight like Alan Shepard or Gus Grissom. So these actually managed to do a little bit of interesting astronomy. The first extragalactic X-ray source they ever discovered was the core of M87, which we now know to have a very large supermassive black hole and a jet coming out of it. They also discovered that the Crab Nebula was an X-ray source, and they discovered a bunch of other diffuse sources. The most interesting source they discovered at that time was Cygnus X1, X meaning X-ray, and it was the first source that they discovered. And this was discovered from the sounding rocket program in the mid-1960s.
And it's also the subject of a song by Rush. A starship gets by and gets sucked in.
Exactly.
Yes.
So following that, one of the problems with this particular system is that you could only get so much observation 5 minutes at a time. And in fact, when I get to the UV, there's an interesting factoid about this. Starting in the 1970s, there was a large series of X-ray telescopes that were sent up, each one with better and better systems, and they discovered things like X-ray sources that were not constant, intermittent X-ray sources, and that was they're able to learn from that how large the sources are. If a source actually changes in brightness very rapidly, they can actually determine the upper limit of the size of this X-ray source. So they could determine, for example, that these things were coming from very small, potentially black holes and that kind of thing. They determined that nova, new stars, exploding stars, would actually produce X-ray emissions. There was the first one that was ever observed was Nova Monoceros in 1975, and Cygnus X1 received a lot more scrutiny. This here is a picture of Cygnus X1 taken by the Einstein X-ray Observatory, which is this one right here. It was HEAO2. They each had little acronyms. This is the High Energy Astronomical Observatory 2, and its informal name was Einstein. This is a picture of Cygnus X1 taken with that, and that, I would be curious as to guess, this was the first sort of picture that actually kind of looked like something, also taken with the Einstein probe in the late 1970s. This is a picture of the Crab Nebula taken in X-rays, and the shock wave of the neutron star at the core of the Crab Nebula produces some interesting X-rays. ROSAT was probably one of the earliest really successful X-ray telescopes, and it actually did mostly gamma ray observing, but it dipped a little bit into the high energy X-ray observing, into the high energy region. So I count that as an X-ray telescope. This is a map of the night sky taken with ROSAT, and you'll notice it's got a very interesting, the different colors were given to the different frequencies of X-rays, the hard X-rays and then the low energy gamma rays. This is, it turns out that comets actually produce a faint glow of X-rays. This is from the particles that are being ejected from the sun hitting the material that is coming out of a comet, and this produces a low flux of X-rays that we can detect, and this is Comet Hyakutake that was detected by ROSAT. And okay, so interestingly, we are again not dealing with a lens that is focusing the light. This is how you focus X-rays. They use what's called a Waltzer grazing incidence telescope, and X-rays cannot be focused with glass. What they do is they use metal cones that are able to deflect X-rays just a tiny little bit. So what happens is an X-ray comes in here and it hits that cone at a very, very shallow angle, and the X-ray is able to be deflected just a tiny bit. And this system is what is used in pretty much every X-ray telescope that is out there, and it's able to produce an actual image. These, if the focal length is extremely long, you can get a very high resolution image of a couple of arc minutes. But what they'll do is they'll take a bunch of these cones. They're called nested paraboloids. They're roughly cone shaped, but they kind of bend in a little bit. And they'll take a whole bunch of them, and the photons that hit those at at various places will actually come together and hit a detector. This is a scintillation screen that actually scintillates like a fluoroscopy screen when it gets hit by X-ray. If you ever go to the doctor and you get a fluoroscope, like an angiogram or that kind of thing, this is the type of detector that you get. It's actually it's got a chemical on a screen that when it's hit by the X-ray, it actually glows, and the detector actually picks that up. Another X-ray telescope more recently is Chandra. It's still up there and doing work. Here's a picture of Jupiter taken by Chandra. You'll notice that Jupiter's Aurora are glowing a little bit in X-ray light. This is a picture of supernova remnant Cas A. This is the one that I guess CAS would be named after. And here's a picture of the most recent X-ray telescope called NuSTAR, which has a very long focal length, and so it has a very good resolution of 9.5 arc seconds, which for an amateur telescope, your tiniest little 2-inch telescope will have a much better resolution than this. But for X-rays, this is actually pretty extraordinary, and you can see all of the nested cones there from the Walzer detector. These are actually the mirrors that the X-rays graze off of, and then they're up in here, and they follow the light path down here to the scintillation detector at the other end. So here's a picture of NuSTAR, and NuSTAR has been, for the first time, able to resolve the X-ray environment at the center of our own galaxy, and it's able to tell when the center of our galaxy actually flares up from time to time. And why does that happen? Because the giant black hole at the center of our galaxy sucks on a little bit of gas, and that material goes into the black hole. The accretion disk briefly forms some X-rays that we can actually detect. Our galaxy is very slightly active. So let's move on to the ultraviolet spectrum. So the ultraviolet is a little bit more. The ultraviolet spectrum is a little bit more familiar to us because a little bit of it actually reaches the ground and has an effect on us, and I will show you that in just a second. So ultraviolet is useful for studying very, very hot stars. The hottest stars in the universe, like the brightest stars are the O and the B and the A type stars. Those produce an awful lot of ultraviolet light. Also, the smaller condensed cores of ancient stars, like white dwarfs and neutron stars, produce a lot of ultraviolet and interacting binaries. Very young stars also produce a lot of ultraviolet light. Planetary auroras, like Jupiter's aurora, also produce a lot of ultraviolet light, just like it does a little bit of X-ray. Our aurora here on Earth produces a very low amount of ultraviolet light. Sky glow has a very little bit amount of ultraviolet light. The sun actually produces quite a bit of ultraviolet light. And very importantly, there are absorption and emission lines of many elements. The elements that make up the stars and make up the gas and dust between the stars actually can glow or absorb light in very specific telltale frequencies that exist in the ultraviolet. The most important one of those is called the Lyman series, which is the detection, which is actually one of the areas that hydrogen gas actually absorbs or emits light. And if we want to detect hydrogen gas between the galaxies, if we want to detect hydrogen gas that is being emitted from the sun and whatnot, the Lyman series is actually a very good way to detect that. It's very much like it's very much like the sequence of emission and absorption spectrum that occurs in the visible spectrum, but that's called the Balmer series. And also another thing that ultraviolet is used for is that gas in space actually diffuses and scatters ultraviolet light really well. So if you want to detect gas that's kind of floating between the stars and is not being illuminated very much, ultraviolet light actually is scattered by that gas really, really well. So if you want to actually detect the gas that's floating between the stars, that's a really good way of doing it. So from our point of view, ultraviolet light is the thing that gives us a sunburn. Our sun actually produces a certain amount of ultraviolet light in what is called in the near ultraviolet. The sunburn is actually in the what's called UVB region, which is a little bit further away from the near. It's just a tiny little percentage of the actual light that gets down here to the ground is a tiny percentage, just a couple of percent of the total UVB light that the sun produces. If our atmosphere were to disappear, there would be 100 times more UV light down here on the ground, and we would all fry. So next time you go out and you get a sunburn, thank our Earth's atmosphere for doing us a favor and blocking out the UV light. Most of that UV light, by the way, is blocked by oxygen that is turned into ozone high in our atmosphere, and that ozone light actually blocks out the harmful UVB light that we experience. Here's a picture of the sky, the diffuse sky in ultraviolet light taken by the Galax probe. This area of orange around here is the universe's UV light in total. The dark areas here are blotted out because they are too bright. This is actually from the hot bright stars in the plane of our Milky Way. But this particular picture was designed to show you what the diffuse gas reflecting the diffuse light of the Milky Way reflecting off the gas between the galaxies and between the stars in our own galaxy look like. This is a region that is slightly higher frequency. You can actually see that there's some texture in it. The individual galaxies and the gas between the galaxies is actually being hit by the light from the galaxies, and that's what this is detecting. So the very first space telescopes were ultraviolet telescopes. They were also sent up on sounding rockets, and the images were taken on this mysterious substance, which is now almost extinct, known as film. They would put a movie camera up in these things and shoot the rockets up 100 miles into space. They would take 5 minutes of observation of the night sky, come down, develop the film, take a look at what they got. And these sounding rockets are still being used to this day to do ultraviolet observation, although not as much, but they were the birth of space telescopes. The very first space telescope that we'd actually think of as a space telescope that NASA put up was the Orbiting Astronomical Observatory. There was an Orbiting Astronomical Observatory 1. It failed on launch, and so they sent a Orbiting Astronomical Observatory 2, and it was sent up in 1968, just a little bit before the Apollo 8 mission orbited the moon. It was sent up in December of 1968. I was just a little tot at that time. So this is a picture of the very first space telescope. It was an ultraviolet telescope. Now, it has a very interesting history. It was proposed, constructed, and run by a tiny little makeshift group from the University of Wisconsin, and this was their laboratory. It was an old garage that they converted into a mission control, and it was just a bunch of people from the University of Wisconsin that asked NASA if they could construct a space telescope. They constructed it and manned it until 1973. It was the birth of satellite space telescopes. It was done from the University of Wisconsin. This is a map of all the targets that they observed. Every dot represents a bright ultraviolet source that they had. Now, this particular telescope did not make images. It actually took spectra of these sources. It would actually go around and find the sources and figure out the spectra of these various sources to figure out what these various things were made out of. Most of these are very bright stars or the cores of bright galaxies. One thing they also discovered was that comets actually produce quite a bit of ultraviolet light, especially in the head and the coma area of the comet. This is a result of the sun interacting with the coma of the comet. And here's a little graph that they showed. They determined that that the hydrogen cloud at 1600 Kelvin was producing a great deal of ultraviolet light. And down here we've got the Lyman alpha measurement, that thing there that I was telling you about. They were detecting hydrogen gas in the coma of the comet from the Lyman alpha measurement, the thing that I was telling you about a little bit earlier. This particular space telescope sort of defined how we think of space telescopes, and this is a Superman comic from the early 1970s. I believe it was 1971, and the picture right here is a picture of the orbiting Astronomical Observatory, the space telescope. Superman ends up using it to destroy his enemy. He throws the space telescope down onto the Earth, and it ends up using it to destroy his enemy. Not long after the orbiting Astronomical Observatory, there was another space telescope that might have been a bit of a step back. This was the Apollo Far Ultraviolet camera, and this was actually a camera that was put on that was operated by the astronauts themselves. They simply set up a little telescope, and in fact, it was not that much different than one of those little tiny Maxitov, like the Meade ETX telescope. And in fact, it had a 3-inch aperture. It had a wavelength that was fairly far ultraviolet. None of this ultraviolet light would actually hit our hit the ground from Earth. It would actually all be absorbed by the ozone, thankfully. And it took 178 pictures of the sky. They basically just pointed it and took a bunch of pictures, took it back to Earth, developed the film. And this down here is a picture of one object. What would you think that is?
The moon?
Not the moon. They're standing on the moon. This is actually yes, exactly. This is a picture of the Earth in ultraviolet. This is the bright ultraviolet reflecting off of the. This is the sunlit portion of the Earth, and this down you can actually see some aurora here, some little ultraviolet aurora on the dark side. And this was an early ultraviolet image of the Earth. If you look very closely at these images, you can actually see that the stars are streaked a little bit. And the reason why is because they needed to take fairly long exposures, and this picture was was pointed at the Earth, but the moon moved during the picture, and because the moon moved during the picture, the stars were actually smeared. Now, up until the OAO2 and the Apollo Far Ultraviolet camera had taken place, all the sounding rockets that had ever been sent into space had taken a grand total of 3 hours worth of observations. Both of these telescopes took more than that on their very first day of observation. So they increased the amount of knowledge about the ultraviolet sky in one day. Over what had been determined the previous 10 years of observation. So this is a picture of the Earth in ultraviolet. This is another picture. This is taken of the. This right here is an enhanced picture taken of the Large Magellanic Cloud, and for comparison, here's a picture of the Large Magellanic Cloud that I cropped and put next to it to compare. This is the Tarantula Nebula up here, and you can see that there's a lot of hot sources along the arms of the Large Magellanic Cloud. So this was done in 1972 on Apollo 16. The telescopes were, not long-term telescopes. The first orbiting astronomical observatory didn't take imagery, but the first telescope that actually took real honest-to-goodness pictures was the International Ultraviolet Explorer. This was the first ultraviolet telescope that took pictures. It had a pretty large aperture, 45 centimeters. That's 18 inches. I have an Obsession telescope that has a mirror that is 18 inches across. That's about the size of a pizza. It did mainly spectroscopic imagery, so it also focused on spectroscopic analysis, but it could take pictures. And what gave it the ability to take pictures was that they developed a technique for pointing it very accurately. They managed to get the accuracy of the pointing down to 2 arc seconds, which is pretty good for that day, not very good for what came later in the Hubble Space Telescope and whatnot. However, it had a very small field of view, only 10 by 20 arc seconds. That's actually smaller than the planet Mars usually appears at opposition. That you would be taking a tiny little slice of Mars. The reason why this is because the detectors they hadn't yet developed sophisticated enough detectors to be able to cover large areas of the sky. It used a very interesting technique. They coated at the end of a cathode with cesium and tellurium, and then they used a normal TV and then the UV would hit the cesium and tellurium and cause it to glow, and then they would use a normal TV camera to video that glow. And so they were indirectly measuring the UV light as a result of the UV causing this cesium and tellurium mixture to glow. Here's a picture of what to give you a sense of the scale. It looks like it's getting cut off here, but this is actually just the aperture. It had an 18-inch aperture. It also had a large number of different imaging systems and spectroscopes. It was the first system to have multiple different detectors for different frequency regimes and different techniques. And here's one of its pictures. This is actually a picture of the core of the Galaxy M87, which crops up a lot in this talk, and you can actually see this is the spectra overlaid on it. There's a more interesting spectra right here. This is a spectra of a comet, Iraq-Alcock, and they were able to tell from the spectrum that there's a lot of sulfur in the cloud around the comet, and hydroxyl molecules, OH. Oxygen, hydrogen. That's if you take and add a hydrogen to an OH, it will form water. There is actually a lot of hydroxyl in water, and hydroxyl tends to be a sign that there is water in this system, in this comet. So they detected the hydroxyl in comets, and that was one of the early detections of that. And that followed up by the Extreme Ultraviolet Explorer. Unfortunately, I didn't have the correct wavelength region here. Sorry about that. And the detection got a lot better. This is a picture in Far Ultraviolet of the Cygnus Loop done by the Extreme Ultraviolet Explorer. You can actually see this is actually the supernova remnant. The Veil Nebula right here. This is a later picture taken also in ultraviolet by the most recent ultraviolet in slightly lower frequency ultraviolet light here. To compare how much better the system got, this is a photograph of the Cygnus Loop taken by that film camera that the Apollo 16 astronauts deposited. There's the Cygnus Loop right there, and this is the sort of network nebula, they call it, the Eastern Veil. There's that little area right there, and this is the Eastern Nebula, which has some ultraviolet light that it's producing. So you can see that the detection got a lot better. This is actually taken by a system known as Galax, which is the next ultraviolet satellite in our journey here. The Galax was known as the Galaxy Evolution Explorer, and the reason why they called it that is because they wanted to detect the hot, bright stars that appear in the spiral arms of galaxies. They wanted to actually figure out where new stars are being born. And this is actually a picture taken by Galax, and this down here is taken by Galax, that one's taken by Galax. And so the Galaxy Evolution Explorer was designed to detect the hot young stars in galaxies. Here's a detector. I love this. This is the only picture of this I could find was a GIF done in 256 colors, and so it's really low res. But this was this is when we're finally getting into the regime of actually having a chip do the observation. Up until this time, ultraviolet telescopes worked by having a scintillation screen. The ultraviolet light would hit that screen, and then they would use visible light detectors to see the glowing of that screen. This was the first of the ultraviolet telescopes that actually had a chip that was able to detect individual photons of light, and they were able to get a much higher resolution as a result of that. This is the near ultraviolet detector. This is the one that actually took this picture right here. The Galax field of view is still pretty high. Unfortunately, they're still not able to get super high ultraviolet resolution, which is sort of unfortunate, but they're able to get really lovely pictures of wide fields. This is a picture of M81 and M82 next to the full moon here, and so you can get a sense for how large the field of view of the Galax telescope is. That's still quite a bit more than the Hubble Space Telescope. So let's move on to our favorite part of the electromagnetic spectrum. This is the visible spectrum. Visible light got a much higher, got a jump start on all other forms of the electromagnetic spectrum because we of course can see it. So human beings have been looking up at the night sky as long as there have been human beings, and this is the region of the spectrum that we are most familiar with. However, it does have it's not just the fact that we can see it that makes it interesting. It has a lot of interesting features to it, and one of the most interesting features is that just about every single element in the periodic table has emission and absorption lines in the visible spectrum. So if you want to tell what the stars are made out of, if you want to tell what gas between the clouds are made out of, as long as they are individual elements, you can actually see the absorption lines and the emission lines in the visible spectrum. So just about every element has absorption lines. H alpha is probably the most famous of those. That is the bright red line that hydrogen gas produces when it is energized by ultraviolet light. And that is in the visible spectrum. It's in the far red. Most stars in the universe have a peak brightness in this region. Stars produce what is called black body radiation. It's the radiation that you get when you heat something up. And the peak of that radiation is a function of the temperature. As the temperature goes up, the peak gets bluer and bluer. There are only a very few stars which have a peak in the ultraviolet. The vast majority of stars peak in the visible spectrum. So if you want to study stars themselves, the visible region of the sky is the most important part of the spectrum for us. The other thing that is great about the visible spectrum is that our technology gives us the ability to create the highest resolution images without interferometry that we can make. So if you want to make a single image that is extremely sharp, the visible spectrum is the best way to do it at this point. Here's a map of the visible sky. As I've been showing you maps of the sky in each spectrum, this was actually taken by the Gaia probe, by the way. It's an entire map of the sky, and we are all very familiar with it. Visible space telescopes started all the way back in 1957, not with rockets, but with balloons. They would actually send up balloons up into the atmosphere, and there was a series of scopes called Stratoscope. There was Stratoscope 1, 2, and 3, and they went all the way into 1971. And the very first one had a 12-inch aperture. The following had a 36-inch aperture, and they were designed mainly to study the sun. They actually wanted to study the spectra of the sun without interference from our own atmosphere, because they wanted to be able to determine very accurately what the sun was actually made out of. And they wanted to be able to take very high resolution images of the sun. So if you've got a 36-inch telescope up against the up high in space, and you're not dealing with the swimming pool of air that we are underneath, then you're going to get a lot sharper image of the sun. So this was mainly its function. However, actual telescopes in space, that are not, hung up by a balloon, they get their start primarily from the space probes that we sent out to explore the outer solar system. One of those, one of the early ones, was the Pioneer 10 space probe. It was the first mission ever to reach the outer planets. It reached Jupiter. It had a very interesting telescope. This telescope was just 1 inch across, and it was basically the equivalent of a camera that had 1 pixel. It was an analog camera, and it had this little opening here, which would trace an image across across whatever it was taking a photograph of. So what it would do is it would scan across and measure the intensity of brightness as it went one line at a time across Jupiter, say, and then it also the Pioneer 11 went on to Saturn, and it would make fairly rudimentary images. Pioneer 10 would send an analog signal back to Earth that was basically just the intensity of the light that it detected as it went across here. I kind of think of this little camera as a Dalek, if you guys know what I mean. It's got that little horn sticking out. Following along with that, the next space telescope of note were the 2 main telescopes of the Voyager space probes, which were launched in 1977. They had about a 9-inch scope and about a 6-inch scope here. And they had a focal length of about, the longer one had a focal length of about 1,500 millimeters. The shorter one had a focal length of about 800 millimeters. And they had a fairly small field of view. I had that written down. The larger telescope had a field of view of about 1.5 degrees. And so it was able to take pictures of a region that was about twice the size, or about 3 times the size of the moon. The wider field telescopes had a field of view of about 3 by 4. So the images that these things produced were produced by something called a Vidicon. This is actually a Vidicon camera, and it's an interesting technology. A Vidicon, they were originally developed for TV cameras. What would happen would be light would hit this little scintillation plate. It would cause that plate to become electrified, and then they would fire off a beam of electrons, and the resistance that the beam of electrons experienced would change as it would trace across the energized plate, and by doing that they were able to make an image. So the more photons would actually hit this plate, the more energized the plate would be, and it would change the resistance of this beam of electrons that would actually pass through this little cathode ray. This is the kind of system that you would have in an old 1960s and late 1950s TV camera. Another Vidicon system is the one that they actually used for the early Apollo missions. This is actually a Vidicon camera here. Here is a raw image from the Voyager space telescope, from the Voyager telescope here. You can see all these little dots. Those are called fiduciary marks, and they're designed to be able to tell the astronomers how to line up the image here. Every once in a while, the signal would get interrupted at the beginning and the end as the electron beam would actually trace across the image. Interestingly enough, this was actually an analog signal. It was not a digital system. It was not a chip that was being used. They would actually, just like the Pioneer system, send back an analog radio stream back to the ground, and then they would reconstruct the image digitally. This gave them the ability to actually stretch the images a great deal, because if you're dealing with an analog system, there's no intermediate light levels and that kind of thing. So you would actually end up with the ability to pull a lot of detail out of these images, and they were able to get a lot of very faint imagery of the rings of Uranus and Neptune, for example, and very faint outer rings of Saturn and whatnot, and that kind of thing. And this is a picture of the planet Neptune. Here's the closest picture that was ever taken of the planet Jupiter by the Voyager space probe, and I just love the old Voyager pictures. These are the raw images, so these are the ones that are not processed. In order to take a color image, they would actually put filters in front of the cathode, and they would take multiple individual images and then combine them in order to produce a color image. So finally, we get to the Hubble Space Telescope, which had been in the works since the days of the end of the orbiting astronomical observatory in ultraviolet. It was originally to be called the Large Astronomical Observatory. It was renamed Hubble in order to go with its, in order to talk about its, in order to commemorate its main mission, which was to determine the Hubble constant. It was the first telescope that would be able to resolve the stars in galaxies that were outside of our local group, galaxies out in the Virgo cluster, and therefore it would be able to determine the expansion of the universe by measuring the brightness of those galaxies and how fast they were moving away from us. It is, to this date, the highest resolution of any of the space telescopes. It has a resolution of 0.04 arc seconds at 500 nanometers. That's roughly greenish light. That's kind of in the middle of the spectrum. That's extremely high resolution. It's very difficult to get that from the ground. It has 47 individual filters for looking at the universe in various frequencies. For example, it has an H alpha filter, it has an O2 and an O3 filter. O2 is singly ionized oxygen, doubly ionized oxygen, magnesium, carbon, calcium, the Lyman alpha region, for example. It can get a few of the spectra of the Lyman alpha region because it actually has a little bit of ultraviolet sensitivity as well. It also has something called a coronagraph, and down here in the corner is a picture of the coronagraph. And the coronagraph is a bar that actually they put out in front of a star in order to be able to determine whether or not there are faint things that are around that. And what they would often do is take a number of different pictures at various angles, blocking out the star each time, and they would add up the light that was around the star and blot the light of the star itself, and they were able to actually determine that a number of stars had gas disks around them, and they discovered a number of Jupiter-sized planets around various stars. Like Fomalhaut, for example, has a Jupiter-sized planet around it. And I'm just showing this because it's a beautiful picture of the Hubble Space Telescope that from the Hubble Space Telescope that I had never seen before. It's quite lovely. So we all know the Hubble Space Telescope. I'm not going to go into it into too much detail, but one thing that people don't know about it very well is that it does actually have ultraviolet sensitivity. It doesn't go very far into the ultraviolet. It goes kind of about halfway that the Extreme Ultraviolet Explorer would go into. But it has the ability to detect Aurora around Jupiter, and this is a close-up picture. And if you take a white light picture, a visible light picture, and you superimpose the auroral picture on top of it, this is what you get. So this is what Jupiter looked like at the time, and this is what the aurora would have looked like. Now the exposure of the aurora would have to be much longer than the exposure from white light, so they don't actually take them at the same time. This is actually taken with a filter that has the emission of hydrogen in one of the Lyman alpha regions. The Hubble Space Telescope also goes into our next region, which is the near infrared. It can take it can go a little bit into the infrared, and infrared gives us the ability to see through gas. This is that famous Pillars of Creation image, M16, the Eagle Nebula, taken in infrared, and this is a picture of the Horsehead Nebula, of course, and infrared gives us the ability to see through gas. So let's go into the region that the James Webb Space Telescope is going to observe in. The James Webb Space Telescope is going to observe in the near and the mid-length infrared. It's going to actually take up much of this part of the spectrum. The infrared region is very interesting because it deals with things that are warm in the universe. So anything that has is not a hot, bright star, but actually has some temperature, matter between the stars, will glow in the near infrared. So warm and hot molecular clouds will glow in higher frequency infrared, and cooler clouds that are far away from the stars will actually glow in deeper infrared. There are a lot of absorption spectrum in the infrared. Particularly, one that's of particular interest to astronomers is carbon monoxide. It just happens to be a very common molecule in space. It's an indication of cooler temperatures. Carbon monoxide absorption is very common, and it's in the very near red. And many other small molecules, water, alcohol, basic amino acids and that kind of thing. Those all have absorption spectra in the infrared. Stellar disks also produce a lot of infrared. What happens is light falls upon the gas and dust between the planets of a stellar system, and that causes the gas to glow. We can actually see the gas around other stars in infrared very well. We can also see stars through gas. So if you want to see the center of our Milky Way galaxy, the stars at the very center around the supermassive black hole, the best way to do that is by looking at them in infrared, because we can peer through interstellar gas in the near infrared. And finally, and this is, I think, the most interesting thing, is we can actually see highly redshifted things. As the universe expands, the further away we get from us, the more the light of an object is stretched into the red and into the infrared and deeper into the infrared. The most highly redshifted galaxies are beyond the ability of the Hubble Space Telescope to see. They are too far into the infrared for us to see the light from them. The James Webb Space Telescope, however, will be able to see further into space, further back in time, by seeing those very highly redshifted galaxies. Astronomers call that high Z redshift, by the way. So this is a map of the night sky in the infrared. This is actually in the near infrared, and most of it is dominated by the gas and dust between the stars, and we have a lot of diffuse regions around it. Infrared changes quite a bit depending on which frequency we observe it in. This is low frequency infrared up here. I'll bring that down. This is, high frequency short wavelength infrared. That's just very in the near infrared, and this is long wavelength infrared. The further you go into the infrared, the more you actually see the gas and dust between the stars, because you're reaching into the cooler and cooler regions of space. So if you want to see the gas and dust between the stars, you want to go long infrared. So one of the first space telescopes that was actually commissioned to observe specifically in infrared was the Spitzer Space Telescope. It was launched in 2003. In order to see things in the infrared, you need to actually cool off the detector. When you're up in space and that telescope is actually getting hit by sunlight. Sunlight up in space will make the metal exterior of a spacecraft be 200 degrees or whatnot. That's actually going to blot out the light from the cool gas between the stars, because it's going to overwhelm it. It's actually going to completely overwhelm it. And so in order to make sure that this particular telescope's detector was able to detect the light of the gas between the stars, it had a canister full of helium gas. which is just a couple of degrees above absolute zero, and the helium gas was going to stay cold for a number of years, and it would give the ability to detect the infrared light. The Space Telescope was actually designed to operate in two phases. It had an initial mission called the cold phase, which was while that helium gas lasted, while it stayed cold, and then they had a warm phase when they would absorb in the near infrared, just a little bit redder than what we can see after that ran out. So the Spitzer Space Telescope operated all the way into the year 2020, doing most of its work in the warm phase. It had pretty good resolution, which was 0.6 arc seconds. That's sort of like if you had a 7-inch telescope here on the ground, that's about the resolution that your 7-inch telescope would get. Its primary mirror, however, was quite a bit bigger. It was nearly a meter across. Took some really lovely pictures. It would take pictures in a number of different frequencies and then assign those frequencies colors. This is a picture of M81 right here and a picture of the Great Orion Nebula. You can see the gas between the stars in M81 right here in this particular picture. Here's a picture of the Andromeda Galaxy taken at 24 micrometers. This is the deepest infrared that it could get. And you can see the gas and dust in if you were to line this up with the Andromeda Galaxy, this is where those clouds of gas are. And you don't see a lot of the stars in the infrared. The infrared light is actually dominated by the gas and dust between the stars. So the James Webb Space Telescope is going to operate in a similar region. The difference between the James Webb and the Spitzer, the James Webb actually goes a little bit deeper into the infrared, first of all. Second of all, it doesn't have that cooling system, so it can operate forever. It's using a shield in order to cool itself, a sun shield. And it cools down to the ambient temperature of the cosmic microwave background that's coming out from the other direction. So it sits here behind the shield and is able to do its detection. Plus, it has a mirror that is much greater. The mirror that the Spitzer Space Telescope had was 83 centimeters, 0.8 meters. This has a mirror that is 10 times larger, 10 times more in diameter. It's 8 meters across. It is the largest and most complex and most expensive and most technologically advanced telescope ever launched in space. And it is wonderful that it is currently actually working very well. Its resolution will be similar to the Hubble Space Telescope at its shortest wavelengths. It's not going to see much into the visible spectrum. The bluest light that it will be able to see is deep orange, basically. Everything bluer than that will be invisible to it. Its mirrors are made of beryllium, which are designed to and have a gold coating on it, which reflect infrared light extremely well, but don't reflect blue light really well. And that's why we see gold as yellow. It has much better infrared sensitivity than Spitzer because its detector has actually been improved, and it doesn't need any active cooling, so it can live forever. It doesn't have a hot phase and a cold phase. It will be out there until it gets hit by a micrometeorite or something like that. So this is a simulated picture of what we might expect looking into the deep universe of the James Webb Space Telescope. And this is just basically what they do, what we will see when we take all of that infrared light and we shift it into the visible spectrum for us to see. It's going to be amazing. So I can't wait.
Did this picture come from NASA? Where did it come from?
This picture was made by NASA, and it is a simulation. It's not a real picture. It's just what they kind of expect to see. So this is if you look at it closely, there's thousands of little galaxies beyond, and those little galaxies are galaxies that are so far away from us that they're flying away from us at very close to the speed of light, and their light is shifted very deeply into the infrared. The next region is a region that is kind of underserved in space for a pretty good reason, because you have to have a very large aperture in order to get a good resolution image, but it has been represented by one particular satellite. This is the sub-millimeter region. Sub-millimeter basically means wavelengths that are less than 1 millimeter. These are very long infrared, short radio wave frequencies, basically. Water has a very deep absorption band in this region, so if you want to do observation of water in the universe, sub-millimeter is ideal for that. There are a few other molecules like oxygen and carbon monoxide which also have absorption and emission spectrum in those areas. This is where very, very cool gas, extremely cold gas, deep in the heart of large clouds and that kind of thing, is actually best detected. Comets actually produce a lot of sub-millimeter emission. They're extremely cold. The surface of comets have some sub-millimeter emission. Most of the sub-millimeter observation has been done by ground-based observatories, because a little bit of sub-millimeter actually makes it down to the ground. We get about, in certain parts of it, we get about 80% of it. In certain other parts, you get about 5 or 6% of that. This is actually the large sub-millimeter array on Mauna Kea in Hawaii, and it's designed to observe that. And these reflectors here are 8 meters across. And in order to get a decent image at that, you need to combine the signal from a large number of telescopes. In order to get a nice sharp image. This is not really practical, sending up an array of sub-millimeter telescopes into space to produce a decent image. And so this has not been one of the regions that has been explored very much by space telescopes, with one exception. This was the sub-millimeter array, the sub-millimeter astronomy telescope, and it was actually created by Japan, and they specifically focused on the detection of water in the sub-millimeter region. They just wanted to find sources of water in space. The next region of the spectrum is the microwave region. This is actually high frequency, long or short wavelength radio region. We call it microwave region. There's a lot of interesting stuff in the microwave region, most notably the cosmic microwave background peaks in this. This is the leftover light from the birth of the universe. If you wanted to be able to detect that without the interference from the ground, from the air above our heads, sending out a telescope in space gives you the ability to do this. We can detect the cosmic microwave background in space. About 1% of it makes it through our atmosphere, and we can actually see it, but there is a lot of interference, and since the interesting details in the cosmic microwave background are extremely subtle, it's a good idea to put something up in space. Microwaves themselves, by the way, are in this region at 12.24 centimeters. This is the frequency at which water and fat actually vibrates as a result in synchrony with the radio frequency. So basically, your box, your microwave is a little box that actually puts out a blast of 12.24 centimeter long microwave waves, and that causes the water in your food to heat up. And so things that are wet will heat up, and things that are dry will not heat up quite so well. You can do an experiment to determine that. The very first microwave telescope was the Comet telescope, and it was designed to learn about the cosmic microwave background. It was the Cosmic Origins Background Explorer. That's what it stood for. It had a giant dish here. It didn't have particularly high resolution, but it was able to determine the frequency of the light coming from the cosmic microwave background. Here's a closer up picture of it here. Here's the dish and the detector here at the center. The most important thing that it did was it actually detected the the frequency of the cosmic microwave background and determined that it acted like a black body spectrum. Black body spectrum, of course, is something that is warm. Like I was telling you before, it produces light at a particular frequency range. The blue line here is the mathematical perfect black body spectrum. If you were to produce an ideal warm object and detect its spectrum, the blue line is what you would get. And then Kobe actually determined that the cosmic microwave background was exactly that. So it was exactly, this was actually really good confirmation that the ideas that we had about the way the universe began were right on target. This was a map of the cosmic microwave background's spectrum here. It was a perfect match. Here's a map of the universe done by the Kobe. The red areas are slightly warmer, the blue areas are slightly cooler. The amount of change amounts to about 1/100,000th of the wavelength. So the difference in temperature is about 1/100,000th of a degree between the hot areas and the cool areas. So it detected, it was extremely sensitive. However, it was not particularly high resolution. This followed on by 2 other satellites which increased the resolution. The next one was the WMAP satellite, which was put up by NASA, and this is the image that it took of the cosmic microwave background, and then followed on by the European Space Agency with the Planck satellite. And you notice that the resolution is getting bigger and bigger. Look over here on the right, this sort of bright blob. You can actually see that this bright blob is reflected. This is the same image, just better resolution. And these are the bumps and lumps of the early universe on which the early galaxies were formed. If the universe had been completely even, if this radiation had been completely even, gravity would have nothing to grab onto and nothing to make new galaxies at the birthplace of the universe. The universe would be very, very boring. But there was slight differences, and this is what caused the universe to collapse. I'm almost done. Finally, we get into the radio spectrum. And the radio spectrum has also not been represented very well by space telescopes. And one of the reasons why that is a good chunk of the radio spectrum is completely visible from the ground. We can see it very, very well. And one of the most important areas of the spectrum is this neutral hydrogen line. This is actually the area, this is actually a frequency that neutral hydrogen, unionized hydrogen, will just spontaneously produce. It's caused by the electrons that orbit the protons in hydrogen atoms flipping from one way to the other. They actually flip, and that produces a very distinct line in space. And we can actually detect neutral hydrogen between the stars at this particular frequency, but we can do it from the ground. In order to make a really high resolution image of space, you need a very, very large telescope, and radio telescopes, we remember the Arecibo telescope can be, several hundred meters across in order to produce a reasonable image of the night sky. You can't put one of those in space. Or can you? There is, in fact, a telescope that is in the works known as the Lunar Crater Radio Telescope. This is actually a planned mission. If you want to make an image of the universe in this region of the electromagnetic spectrum, where the wavelengths are much longer than 10 meters, 10 meters on up, you need an extremely large detector. And there's a plan to send a little rover into a crater and use the bowl of a crater to suspend this wire mesh, kind of looks like a Spider-Man's web, in order to create a very, very long wavelength detector on the far side of the moon. one of the advantages of this will be is, you know, the human-based radio, the human-based radioactivity will be blocked by the moon itself. We actually do quite a bit of interesting communication in this. Communication with submarines is done in this range right here. Shortwave radio is done in this range right here. AM, FM, and TV signals are in the region that are that we can actually see through Earth's atmosphere. So this will be a good place to actually do radio astronomy. There has been one space telescope that was put up by Japan. It was called the Highly Advanced Laboratory for Communications and Astronomy. It was put up in 1997. It was a test system, and it was done at fairly short wavelength radio frequencies. And this is a picture yet again of the core of M87 done in radio light. They sent up a satellite here, and it operated in just the year 1997. It was 8 meters across, and it was a test of the technology. It didn't actually do a lot of observation, but it's possible to actually put radio telescopes in space, and this was determined by that. Here's a little picture of the planned system. This may happen sometime, you know, in 20 years or so. It's not really funded at the moment, but it's something that astronomers want to do. Yeah, little rover will trundle down into the bottom and run a wire across, and run a bunch of little wires, and they'll make a parabola out of these wires hanging down. So anyway, that is the history of space telescopes. If I were to have given you a list of all of the space telescopes that ever existed, this talk would have been about 20 hours long. There have been dozens and dozens of them, and I have focused mainly on the ones that were put up by NASA. I mean, the Russians and the European Space Agency and Japan and a couple of other, India and such, have put up a few space telescopes as well, and it's very well represented. So anyway, I have some time for questions if anybody's interested, and I appreciate you guys all sticking around. I know I talk a long time, but I appreciate everybody's attention.
Thanks, Brad. I found your talk absolutely interesting. I was not aware of how much had been done before we had our World Wide Web and all of our information sharing.
Well, thank you.
Yeah, I didn't know there was that much of it either. This was great, very interesting and well put out.
Yeah, the one thing I was surprised to learn about was the history of how they started off by using sounding rockets. I mean, it strikes me as astonishing that in the late 1950s they were able to actually do detections of X-ray and ultraviolet sources on a rocket. You know, they were able to point the rocket on the nose cone or point a detector on the nose cone of a rocket that was flying ballistically, and they only had a few minutes to do it. You know, they were able to do actual observations. Cygnus X1 was detected by a sounding rocket, which is pretty extraordinary.
Why were they called sounding
rockets? Well, they would originally send them up in order to detect the properties of the upper atmosphere. That was the original mission, and that was called sounding. They would actually reflect radio waves off of what they put up there into space. And so they didn't go out into the upper atmosphere. They stayed in our atmosphere at a point at the region where they would actually reflect radio waves up off of the upper part of the atmosphere. So it was just based on where they were.
The balloons.
I'm sorry?
As far as what they could detect, the range, or how limited were they?
Well, the balloons were actually able to get better. They were able to work for longer periods of time. They focused mainly in the ultraviolet, X-ray, and some in the visible spectrum. The big issue with the balloons is that they get jostled around, and the stabilization was a little bit harder. And so they weren't able to get very, very long exposures. They took, individual little snapshots. The ultraviolet and the visible imagery that was actually taken by the balloons was done in the era of film. So they had to contend with the fact that if the telescope got jostled around during the observation, that it would smear the image that was taken with the film. And so there was some limitations to balloons. Rockets, interestingly enough, could be stabilized with gyroscopes a little bit better, and even though they took shorter exposures, they could get almost as good of imagery from rockets as they could from long-term balloon flights. So,
But the balloons were high enough that they got a fairly wide spectrum.
yeah, the balloons went up above most of the atmosphere. So the balloons would go up like 100,000 feet to be able to get over most of the Earth's atmosphere. Yeah,
Okay.
20 or 30
Brad, there's
miles.
something else I have read about. What about these space telescopes that have flown in these U-2 jets? Some of them collected dust from out high in the stratosphere.
Oh yeah. Okay. So there's a real interesting there's an astronomical observatory known as Sophia. I didn't want to. I had to limit myself because I already talked for an hour and a half. Sophia. But there's one called the Sophia Telescope. It was actually, I think it lost funding recently. It's an 8-meter telescope that's in the back of a 747. Let me share my screen here.
They got some in these old U-2 jets too.
Yeah, there were some early ones that flew real high. The Sophia. So when you go into the stratosphere, Sophia, the S of Sophia means stratospheric. Let me share my screen again here. This is let's see here, share, and okay. So Sophia, this is what it looks like. Here's the observatory here, and it's got this window on the side where they fly a jet up into the stratosphere, and they're able to take observations from the back of a large jet. This gets deeper into the infrared. They can do some adaptive optics type work. They can do fairly high resolution imagery. This is another technique for getting a little bit better. They're not completely getting all of the infrared light, and they can't go too cold because the atmosphere itself actually has temperature. You're looking through Earth's atmosphere, and so you can't get something that's colder than Earth's atmosphere. You can't actually see the light from something that's colder than Earth's atmosphere. So this is another technique that they're using right now. There's also a few other systems. There's one that they, like James said, put on U-2 telescope, that because the U-2 spy planes were actually that were actually very high. That's not used anymore. That was in the mid 70s that they did that. I'm trying to I'm seeing I didn't want to get too far into that because there was here's the some of that imagery.
Ireland's best export.
Yeah. So
seen them twice.
Yeah. One of the things with Sophia is pretty extraordinary because they have a really amazing gyroscopic system that is able to actually take real honest to goodness pictures. I mean, they're able to cancel out the motion of the airplane really, really well. With the U-2, it's the plane is much, much smaller, and they don't have the ability to have this large gyroscopic system. They can put an 8-meter telescope in the back of a 747. You can't put an 8-meter telescope in a U-2 spy plane. So
well, right, and the U-2 and the Blackbird were both their cameras were pointing at the Earth, not at the stars.
Well, yeah, I mean, they had actual astronomical observatories in U-2 airplanes.
Oh, yes, they did.
They were designed
They
to look
did.
down and not up. But when
Right,
in
so
later
they're interested
years
in
when
something very different.
yeah, this was just an experimental technique. The Hubble Space Telescope, its optical system is based very closely on spy satellites. There was a system of spy satellites that had similar aperture to the Hubble telescope. There is actually a new telescope called the Nancy Grace Roman Space Telescope, in which the system is actually, the backbone of the system is actually an old spy satellite, and it's going to have a very wide field of view. That's going to go up in probably the next 5 years or so, and Hubble is exists because of the military system that it was based loosely on. So.
Hey, Brad, I have a question. You're speaking about the Hubble and stuff. How can the data back then, which was a lot smaller, versus the data today, which is very specific, how can that data back then affect our data today?
I'm not sure I understand. So.
Like it wasn't like. Some of the graphs you showed were like just little dots, and now we can use statistics and algebra and different things to get things down to nth numbers.
So why have we gotten? I think if I'm understanding you correctly, why are the systems able to resolve much more, do much more today than they were in the past, and that's because, of course, the detector technology has gotten better. We've committed more resources. We've learned how to make space telescopes better over time. The older data is, I showed you the data that was as it was when it came out. The data hasn't gotten better since then. We've just been able to present it in a new way. For example, the Voyager imagery, for example, with digital processing, we're able to take all those little fiduciary marks. We're able to fill in the gaps between the where those dots are. We're able to enhance the images a little bit better with digital technology and that kind of thing, because we have computers that are able to take those images and work with them, software that has been developed in recent years. But the amount of data that we've gotten from that old stuff has not changed since that time. We're still working with the data that was sent back. So.
Thank you.
Okay. Well, thanks, guys. I appreciate it. I realize that I do talk for quite some time. I have that habit, but I appreciate everybody hanging out, and I hope we get some clear skies, and maybe we'll be able to meet at the next meeting. So.
Great talk, Brad. Thanks for all the work.
No problem. Thank you.
That was great, Brad.
Excellent. Good job.
Thank you, Brad. That was a great presentation.
Thank you, guys. I appreciate it.
Thank you, Brad. As always, a great job.
Thanks.